usually for a talk like this, like a physics colloquium at a university, I talk about the science first, and then I try to leave the education and outreach till the end. And I'm going to move that up front and point out a couple of things that astronomy educators could potentially be interested to bring into their classrooms. Then I'll talk about our observatory science goals. Thanks a lot. Our observatory science goals, sort of the status of the observatory, how we measure properties of very high energy cosmic rays using detectors on the ground, two different types of detectors. I may not have time to go through all of the physics results because I mainly want to dwell on an article that we published in Science in 2007, which showed a striking correlation between the arrival directions of the highest energy cosmic rays and point sources out in the sky, other galaxies, but not any old galaxy, particular galaxies that are called AGNs, that have an active galactic nucleus probably at the center. And what's also happened to that result as we've continued to take more data since 2007. But if I have time, I'll talk a little bit about the energy distribution for primary cosmic ray particles and something which is called the GZK suppression that I will explain what that means. And then some sort of question marks we have about what we're seeing in terms of what are the primary particles that are coming to us from these other galaxies. Are they protons? Are they light nuclei? Are they heavy nuclei like iron? If I have a moment, I'll talk about the involvement of our group in the experiment. So here we are, down in Argentina. Twice per year we have a collaboration meeting where about a third of the 350 or so collaborations show up. It's a international collaboration with all 13 different countries and all of these institutions from the United States, including Nebraska. So I was at that collaboration meeting, and I just wanted to mention the two founding fathers of this experiment, Alan Watson, a cosmic ray physicist from Leeds in the UK, and Jim Cronin, an emeritus professor from University of Chicago that won the Nobel Prize. So Jim has to do with why I got involved in this experiment, which has been one of the most fun scientific projects I've worked on in my career. As Kevin mentioned, here in Nebraska we have this high school-based cosmic ray network, and we inherited scintillation counter detectors to recycle onto the rooftops of Nebraska high schools from a previous cosmic ray experiment of Jim Cronin. So in 1999, I'm sitting in my office, telephone rings, pick it up, it's Jim Cronin. I knew him from past interactions, and he said, I know you like this high school cosmic ray outreach. Would you like to become the education and outreach coordinator for my new project in Argentina? Well, I thought for about 2 nanoseconds and said yes, and it's been such a nice experience with this experiment. I've learned a lesson, which is when a Nobel Prize winner calls you up and says, do you want to work on my experiment? You say yes. So here's where we're located. In the high plains of western Argentina, just east of the Andes, which separate Argentina from Chile. The site selection was done before I joined the experiment, but they did happen to put it in the wine-making region of Argentina, so that adds a little bit of interesting fringe benefits from going to collaboration meetings there. Now, getting there is no picnic, although our speaker a little later on from Ice Cube will tell us that this is nothing compared to the travel that those people do. But anyway, getting down there is a 2-hour trip from Omaha to Atlanta, 10 hours to the capital of Chile, Santiago, one of the most beautiful flights you can take in all of the world from Santiago across the Andes to Mendoza, and you fly right by the highest mountain in the Andes called Aconcagua, and then you have to, after traveling all night, rent a car and drive 5 hours to the experiment. So it's a lot of travel. Okay, so let me I do give 45-minute, hour-long talks just about the education and outreach initiatives that we do in the experiment. I've been the outreach coordinator for a little over 10 years now, but I just want to mention a couple of things. In the observatory headquarters, which is located right here on the ground floor, we have a visitor center that seats about 65 people. This is one of the mirrors from one of our fluorescence detectors that I'll show you later. Kids really love to stand in front of that and see themselves right side up or upside down, depending where you are with respect to the focal length. This visitor center has hosted over 65,000 visitors since opening in 2001. It's really been kind of a scientific tourism attraction in that part of Western Argentina. The experiment also partnered with the province of Mendoza and the city of Malargüe, where we're located, to construct a new school that they named after James Cronin. This is the opening in 2007. There are lots of schools in the area that either don't have the resources to travel to Malargüe or the distance is too far. So we've also started what we call the Rural School Program, where observatory staff members volunteer to go out to these remote schools, give them science presentations, and then often these schools are not well outfitted. Like this school didn't have heating during the winter, so here we're donating to them last December a bunch of electric heaters so that it's more comfortable in the school during the winter time. About every other year, we did it in 2005, 2007, and 2010, we sponsor a science fair in the observatory headquarters. Here's one of the ones, I think that's from 2007. Here's Jim Cronin with some of the participants in one of the projects. It's a really very nice in-house event where collaborators serve as judges and prizes are awarded and so forth. That's been really popular. Now, the thing that might interest you is the following. We decided within the collaboration to release on our website, here's our website here, 1% of the recorded events, and we reconstruct them so that students and general public teachers don't have to deal with the raw data. They get reconstructed quantities like the energy of the cosmic rays that we measure and the direction of the sky from which they come. That's available in 5 languages. It's really quite popular. We get about 4,000 hits per year. And it's been used by a lot of different students and teacher groups. Here are 2 students from a high school in Colorado that went to our website, used that data, and won a science fair based on the physics distributions that they were able to make from our publicly released data. So basically using that data, although the statistics won't be that high, you can make any of the physics distributions that I'll be showing as I go through this talk. All of us collaborators were all physics professors and educators, and so when we go to Argentina, we often put on courses for local science teachers, teaching them about some of the more modern, like hands-on, experiential teaching. So that outreach has been really successful. Actually, integrating ourselves into the community, we've had a positive impact. The collaboration even takes part in local traditions. Like every year, there's an annual parade, and we get behind a banner and walk down the middle of the street. And it's really sort of fostered a sense of partnership in our scientific mission. One piece of evidence of that is we have these detectors that are spread all over the desert on people's properties, and we have very little vandalism. We think that the local community sort of has ownership, and they're partners with us in our scientific mission. So that really has been a great success. With this experiment, our science objectives, we want with unprecedented statistics, measure the cosmic ray energy spectrum at the very highest energies that have been observed. We have actually seen this predicted GZK suppression that I'll show you in a moment. The thing that perhaps has had the most publicity is this arrival direction distribution and the correlation of those arrival directions with certain special galaxies that are actually fairly close to us, within about 200 million light years of us. And then we have some studies and some confusion actually about what we're observing when it comes to the composition. That means what types of particles are those that are coming to us from other galaxies. We'd also like to see if we can bring in on some potential theoretical models which try to explain how these extremely high energy particles come to be. There are sort of two different classes of models. There's a conventional model of bottoms up, which means the particle you see, let's say it's a proton coming to you from another galaxy, it started as a proton in some astrophysical catastrophe at some other galaxies, like galaxies colliding, or now we know that there's some correlation with hot galaxies with an active galactic nucleus. So these are basically, these particles are accelerated in some big shock wave or catastrophe. There are other sort of exotic top-down, we call them, scenarios where there are these heavy objects floating around in space, maybe relics of the Big Bang, and these heavy objects decay to these particles that have very, very high energy. Now the thing is, with those types of exotic scenarios, we expect, there's some other stuff here. We expect there to be observing some number of photons and neutrinos as the primary cosmic rays, and we're already setting limits on the flux of high energy neutrinos and photons, which are starting to rule out some of these exotic models for the existence of these highest energy cosmic rays. So there's one of them. Okay. If you give a high energy cosmic ray talk, you're sort of obliged to show this decade-old plot made by Simon Swarty at the University of Chicago, who unfortunately passed away over the last year. What this is the flux or the rate of cosmic rays that we observe on Earth versus energy, and you can see that this is a log scale. Here's 10 to the 9th electron volts up to 10 to the 20th electron volts. And the flux is also log, so that means it's a power law. But you can see that there's some structure in this distribution. There's what we call the V, where the flux gets steeper. The slope of this is a little steeper, and then there's something called the ankle, where it gets a little bit shallower. Now, I'll point out some interesting numbers here, which is those highest energy cosmic rays come very rarely. Up in this energy range, you get about one of them per square kilometer per year, and that's why in order to have enough statistics you have to make a big detector, and that's what we did down in Argentina. So what do we understand about how particles reach these energies? Well, Enrico Fermi calculated that an exploding supernova at its shock can generate high energy particles emitting from it that would only go up to about 10 to the 15th electron volts. And you can see that we have, we observe energies much higher than that. We also kind of interpret this ankle here, where the slope gets a little shallower, as perhaps a transition from cosmic rays coming from our galaxy versus cosmic rays coming from other extragalactic sources. At the Pierre Auger Observatory, we focus on the highest energy cosmic rays up in this range, where we really don't know what the acceleration mechanism is, and these cosmic rays we call ultra-high energy cosmic rays. Okay. Let me just mention a little bit about what this thing is in the energy spectrum that we anticipate seeing, and we've now confirmed it, called the GZK cutoff. These gentlemen, you remember the cosmic microwave background radiation that was mentioned in the talk, in the LIGO talk yesterday. These are cold photons at about 3 degrees Kelvin that are relics of the Big Bang. They permeate the universe. So, of course, if a high energy cosmic ray is going to make it from a remote galaxy to here, it has to go through that cosmic ray background, the microwave background, and particles traveling long distance will lose energy via collisions with this CMBR. The dominant process, as you can see that it's a little dark, is a proton hitting one of those CMB photons, giving either a proton or a neutron, or a plus a neutral or charged pion. Okay, so what that results in, if you do all the calculations, is that the energy spectrum here on Earth for primary cosmic rays greater than about 5 times 10 to the 19th electron volts should be suppressed. Okay. Now, I'll just point out that until Auger came along, there was controversy about whether previous experiments were seeing that GZK suppression or not. One experiment in Japan, called the Agase experiment, showed a slope of the flux distribution versus energy that didn't seem to be falling off, and then an experiment in Utah called HIRES was starting to see that. But it's not so convincing with the statistics. We've totally nailed this down now in the Auger experiment with 10 times more statistics than either of those experiments. Okay. We're interested in, of course, in the properties, the energy, the arrival distribution, and so forth, of the primary cosmic rays that are coming to us from outer space. So that object that's entering the atmosphere. When that particle hits the atmosphere and starts having collisions with molecules in the atmosphere, it's completely destroyed. Okay? So we learn something about this primary cosmic ray by observing the properties of this, which we call an extensive air shower. Okay? How does that happen? Just like in experimental and particle accelerators, when two particles collide at very high energies, you get a bunch of secondary particles. Those secondary particles are energetic enough that they themselves can have secondary collisions with other air molecules, making another set of particles. We call that an avalanche or an air shower. By the time that all of those collisions happen, you could get something like 100 billion particles at sea level, mostly muons, photons, and electrons. And the interesting thing to observe is the large area on the ground, which is the footprint of that extensive air shower. Something like 6 kilometers by 6 kilometers. You know, that's basically the size of Lincoln, Nebraska. So there are times when Lincoln, Nebraska is totally lighting up with billions of particles from high-energy air showers. Okay? Now, that's a computer simulation, but just kind of as an educational aside, there's all sorts of modern physics that you could illustrate by the existence of air showers, okay? Including creating new particles via E equals mc squared. The energy of that primary cosmic rays goes partly into the mass of those secondary particles. You could talk about unstable particle decays, because among these particles are, say, muons and pions that decay. You can talk about probabilities and interaction lengths of one of those shower particles until it hits the next air molecule. You can talk about statistical fluctuations. All of these processes are not unique, but there are lots of statistical fluctuations. And in particular, it's a great illustration of time dilation. All of these particles are ultra-relativistic. So muons, for example, that are created, they are time dilated so long that they reach the ground before they decay. So there's a lot of that kind of interesting stuff that you can talk about when it comes to air showers. What can we learn about the primary cosmic ray by looking at the distribution of particles hitting the ground? And what we do, you'll see pictures of this, we put a grid of detectors on the ground. We only sample those air shower particles as they hit the ground. But the statistics, those 100 billion particles, it's enough that if we count the number of secondaries that reach the ground, that's proportional to the energy of the original primary cosmic ray. I'll show you in a second. The relative arrival times of these particles at the different detectors tells us about the incident direction. And then the depth of what we call the shower maximum is related to what type of particle that is. What do I mean by the shower maximum? You get, early in the shower, you get more and more particles because the particles are energetic enough to create new particles and new collisions. But eventually the secondary particles are not energetic enough to create new particles, so then the shower kind of peters out. So somewhere along this longitudinal distribution, there's a maximum in the number of particles, and hence a maximum of the energy deposited in the atmosphere. How do you determine the direction from the arrival times at the different detectors? Okay, here's a picture of an incoming, that's the original direction. These are the particles in the air shower. They sort of form a curved pancake as it projects down on the ground. And so I actually like to illustrate it more with something like this. Okay, if you have an air shower coming from straight above, those particles are going to project themselves on the ground basically all at the same time. So you'll have the same time recorded in all of the detectors on the ground. But if your air shower is projecting in from the side, it'll project onto the Earth like that. So these detectors will get hit before those detectors, and those time differences allow you to point back the original arrival direction with a precision better than 1 degree. We use two different types of detectors, actually. This is just an artist's cartoon of one of those air showers. Here are the air shower particles developing in the atmosphere, and then we actually detect a fraction of those particles in a set of Cerenkov detectors that we have on the ground in a grid. We have many, many of these. But another thing that happens is as those relativistic particles streak through the atmosphere, they make the atmosphere fluoresce in the ultraviolet. It's the nitrogen molecules in the atmosphere that fluoresce. So we also measure that fluorescence light with other detectors that are encircling or surrounding the array on the ground. Here's a picture of those two types of detectors. This is one of the detectors on the surface. I'll tell you more about that. And this is one of those fluorescence detectors. That fluorescence light is very light, very, very faint, sorry. So it would be totally overshadowed by sunlight or even moonlight. So we only open these garage doors on the fluorescence detectors on clear, moonless nights when we're sensitive to that ultraviolet light. So the duty cycle of the fluorescence detectors is about 10%. The surface detectors, those operate 24/7. Okay. Here's a little cartoon, if you can see it, of one of these air showers developing. Here are the actual air shower particles in that plane projecting themselves on the surface detector tank. So we get signals in several detectors on the ground. And then the fluorescence light emanates in all directions, and then on those fluorescence detectors you get these streaks of ultraviolet light detected by the photomultiplier tubes in those fluorescence detectors. So we have two independent ways of looking at that air shower. Okay? It is a big array. We have 1,600 detector stations spread over 3,000 square kilometers. That's about the size of the state of Rhode Island. The spacing is 1.5 kilometers, about a mile between each of those detectors. And then this region is surrounded by four of those fluorescence detector buildings. Each of those buildings has 4 telescopes. I'll show you what those look like that look out over the array. I hired a private pilot in a small plane in 2006, and I had him fly me over the entire array, mainly so that I could take pictures of those fluorescence detectors and this beautiful desert in western Argentina where the experiment sits. There is an atmospheric monitoring station called the LIDAR station that stands for Light Detection and Ranging, and I just show you that because our group is involved in the atmospheric monitoring done by those devices. I probably won't have time to get to it. When we outfitted the very last tank number 1600, everybody signed it, and then it went out onto the field. Let me show you how those detectors work. These things are sitting out in the middle of nowhere. You can't have an AC power cord going out to power them, right? So this thing is a tank full of 12 tons of purified water. The water is viewed, it's light tight inside. The water is viewed by 3 photomultiplier tubes. When the cosmic ray particles pass through the air and through the water and into the ground, they generate Cerenkov light in the water. Those flashes are detected by the photomultiplier tubes. But you need electricity for that, so we have solar panels there, which charge up battery boxes. Those battery boxes power the electronics in the electronics enclosure. There's a GPS antenna. The role of that GPS antenna is twofold. The GPS signal tells us not exactly where that tank is and whether it's moved around because of an earthquake or something, but it gives us a very precise time that tells us when this detector got its signal. All that information, when we have an event detected by one of those detectors, is transmitted via a communications antenna. It's basically cell phone technology. It makes a call to the data acquisition center saying, look at me, I've got an event. And then if there are other tanks in the area that also have events close in time, then that information is, then the information from all of the detectors is ready. That's kind of what our trigger is all about. It was quite a challenge to install all of those detectors. We have an assembly building where we put everything together. We put them on a truck and take them out onto the desert, place them on the ground. That's a water tank that fills it up with pure water. Oddly enough, the place where we are, it kind of mysteriously floods from time to time. So there are challenges associated with that. Once you have the water inside, then you come and install the electronics and make sure that it's working. Here's a weird, interesting thing, okay? Cows like these detectors. Okay? Like a group will go out to repair a detector and we'll find like a bunch of cows sitting around. And we're trying to figure out why. It could be that like in the early morning and in the evening it's the only shade that's around. So maybe they like that shade. Another thing that we noticed is that when we first designed that battery box, it had like square, like right-angled corners on it, right? We'd go up and find those things broken. Sometimes there'd be a little cowhide associated with it. We think that the cows were scratching their shoulders on the battery box. So subsequent to that, we like re-outfitted the battery boxes with like rounded corners. Okay. This is a quick picture of the fluorescence detector. We call them fluorescence telescopes, but what they really are is mirrors that look out in the sky through a UV filter and a corrector lens. The fluorescence light that comes into the mirror is reflected onto a battery of, we call them, you know, it's pixels, but it's 440 photomultiplier tubes that record the streak of ultraviolet light as the shower passes through the atmosphere. Now, those fluorescence detectors are perhaps the real strength of our experiment, because by themselves, the fluorescence detectors make a better energy measurement than the surface detector arrays because of the fact that they're able to, quote, see most of the shower profile, right? This is the number of shower particles versus depth in the atmosphere. I mentioned how the particle density increases, reaches the maximum until those particles aren't energetic enough to make more secondary particles, and then the particle distribution peters out as it goes like that. So the fluorescence detectors really get a view of that whole longitudinal development in the sky. I'm going to skip these details. This is sort of how we transfer the calibration that we get from one set of detectors to the other set of detectors. But what's really interesting is what these showers look like. This is an event display from the computer that shows an event where one of those showers struck 18 of these surface detector tanks. Imagine, those things are a mile apart, right? You stand at one of those detectors, you can barely see the others that are a mile away. And then just to think that there's this phenomenon where a cosmic ray comes in and lights up 18 of those detectors, it's just truly amazing. It's one of the fascinating things about it. The way we determine the energy with the surface detectors is that we determine from how many particles are seen by all of these different detectors where the core of that shower is, the place where you have the highest number of particles. That'll be the detector, if there is one right there, that has the highest number of the highest signal size. And then we plot the signal size in all of these other detectors as a function of the core distance. And then we choose one place, 1,000 meters from the core, and that's our energy distribution for that event for the surface detectors. But that's in arbitrary units. we have to convert it to real energy using information we get from the fluorescence detector and its calibration. We also have really great events that we call hybrid events, where the shower is seen by both types of detectors. Here's an event display where a bunch of surface detectors were hit, and then this fluorescence telescope in that bay, in that garage door, had this streak of light. And then what this shows as a function of depth in the atmosphere viewed by that fluorescence detector, how many particles or how much light was seen. And so you can see the numbers of particles increasing, reaching a maximum, and then petering out on the other side. The integral under that curve is what gives us the best energy measurement for one of those showers. We have some fantastic events that hit the middle of the array where you see the fluorescence light in 1, 2, 3 different detectors, and then this is our golden public relations event. This was actually on the poster of the American Physical Society meeting in 2010, I guess it was, this very event, where a lot of surface detectors saw signals, and then all 4 of the fluorescence detectors saw a signal. Okay, so I can tell now that I'm only going to have time to talk about the main physics result that was published in 2007, and kind of what has happened with that result over the last couple of years. So it's probably the only time in my career that I'm going to be a co-author of a paper in Science which makes the cover story. We got a lot of publicity for this. It was by Science. They said it was the 3rd most interesting scientific breakthrough in 2002. I really like this one. You know also of the prestigious journal Nature. They said it was one of the top 10 science stories not published in Nature. I also got so then there was press coverage all around the world. These are 2 papers in Argentina. The discovery was announced. It happened on the day that the woman president of Argentina met the woman president of Chile for the very first time. But we were right there with them with our discovery of Misterios Astronómicos. I also got a little bit of airtime, 15 minutes of fame here at the university, where our faculty newspaper and Daily Nebraskan said that I helped, discovering the source. I can skip that. I show this only because I'm going to show you a plot of our data in galactic coordinates. So when I talk to students, I have to tell them, where does the galactic coordinate system come from? So I show them a cartoon of our galaxy, the fact that it's a flat spiral galaxy. I say galactic coordinates is based on a plane that you draw through the center of mass of the galaxy. So you split the universe into objects that are above the plane of our galaxy and below the plane of our galaxy. I like to do that and show it before I show this results plot. This is the results plot in galactic coordinates. So here's the center of the galaxy along here. So this is above the center. This is above the galaxy. This is below the Milky Way galaxy. I also superimpose on here the supergalactic plane. Let me just tell you briefly what this is about, and I'll skip some of the reading of the details. One of the interesting things is that one of the closest galaxies that has an AGN, it's only 3.4 megaparsecs away, is Centaurus A, and this is the location of Centaurus A in this coordinate system. Okay, the circles on here are a set of about 25 of our highest energy events. It's the arrival directions of those events. And then also plotted on here are all of these red crosses. These indicate the locations of special galaxies, the ones with an active galactic nucleus. Okay, and what you see, I think I'm going to skip the slide that goes into all the numbers and the probabilities and so forth. But what you see is about half of our arrival directions point right at active galaxies with AGNs that are pretty close to us, within about 75 megaparsecs, or about 200 million light years from us. And so that correlation was really significant, and that's why we basically were saying we're starting to see where Lee's highest energy cosmic ray come from. Not just from any other galaxy, from these special galaxies called AGNs. I'll just point out that AGN, only about 1 in 1,000 galaxies that we can see has an active galactic nucleus. theories. I'll skip this details of the probabilities and how many events correlated versus how many events would have correlated if they were coming from just isotropic sources in the sky. Just a little image about Centaurus A. But I like to show this because this is the same result plotted in a different coordinate system. This is Earth equatorial coordinates. So the equator of the Earth goes through the center of here, and the round circles represent our measured arrival directions. These are those galaxies with active galactic nuclei in that coordinate system. What you can see is that, well, we're located in the southern hemisphere, so we're seeing things that, we're seeing arrival directions. Here's Centaurus A over here that you can see from the southern hemisphere. And then I just want to show you that something really puzzling has happened. We don't know if we were lucky, if maybe we've had some kind of problem with our measurements at the observatory since this first measurement, because over the last couple of years, since we published that paper, the degree of correlation has decreased. And we don't really understand that. We don't think that those active galactic nuclei sources have like turned off or something in the last couple of years. So what this is the fraction of events correlating with the AGNs in the certain catalog of active galactic nuclei. At the time that we published, we had 20-some events. So like I said, about half of our arrival directions were correlating with certain AGNs that we know. But now, we still have a correlation that's, would be the correlation if the arrival directions were isotropic, coming from everywhere. We still have a noticeable correlation with those AGNs, but we're really puzzled why over the last couple of years we haven't seen a continued or like a stronger correlation with these active galactic nuclei. So the last thing I want to say, and then I think I'll go to my conclusion and skip the results. I can talk to you later and answer questions about our energy distribution and so forth. But why did we build this experiment in Argentina in the first place? It's because from the southern hemisphere, you have a better direct view of the center of our Milky Way galaxy compared to the northern hemisphere. And we wanted to answer the question, is there a black hole? Does the center of our galaxy, of our own galaxy, emit high energy cosmic rays? We found something interesting. Our claim is that it doesn't. Okay, there's not an excess of high energy cosmic rays coming from the center of our galaxy, which is somewhat in conflict with previous claims that have been made by other cosmic ray experiments, where especially they saw 4.5 sigma excess in a region. Okay, here's the center of our galaxy on these different plots. This is our data, sort of over density significance. We're really not seeing any major enhancement coming from the center of our galaxy. All right. I guess the last thing I'll say here is that we really feel that this is the beginning of cosmic ray astronomy, okay, where we can not only look at galaxies in the infrared and the radio, but we can actually look at high energy charged particles coming from these sources. We just need more and more statistics in order to be able to do that. I think just in the interest of time, I'm going to skip. This is interesting physics. It's all about the energy distribution and the particle composition, what we're learning about if these particles are protons, iron, whatever. I'll just summarize it by saying, with the best statistics ever, we've been able to confirm the existence of this GZK suppression in the energy spectrum. We've identified extragalactic point sources, galaxies, special galaxies with AGNs. We've studied the particle type of the primary cosmic ray energies, and I really think that there's lots of education and outreach opportunities related to the observatory, including students, teachers, classes, working with that reconstructed air shower data that we released to the public. Thanks a lot.